So from previous lectures, we know now how to solve the Dirichlet problem in the unit disk by the Poisson formula. However, the Poisson formula is quite cumbersome to use. And in certain situations, the same problem can be solved in a much easier way by using conformal maps. So let me take an example here. Consider the situation where we have the unit disk in the complex plane, and then we want to find a harmonic function which is 1 on the upper half of the boundary here, and -1 on the lower half. So in principle, we can now insert these boundary values in the Poisson formula and compute, but it's not a pleasant calculation to do. So a much easier way to do this is to map the unit disk onto the right half plane. So this region is mapped onto this region then. And we know how to do that. We can do it, for example, by the map W equal to 1 plus Z divided by 1 minus Z, where, well, Z is the coordinate over here and W is the coordinate over here. And then it's easy to see now that the upper half of the unit circle is mapped onto the upper part of the imaginary axis. And the lower part then is mapped onto the lower part of the imaginary axis. So the idea is now to, instead of using the Poisson formula here, we find a harmonic function in the right half plane which takes the values 1 on the upper half here and -1 on the lower half. And as it turns out, that is very easy to do because we almost already have that function. Consider the argument, the principal branch of the argument function. We know that the argument of any number on the upper half of the imaginary axis is pi half, and then the principal argument of any number on the lower part of the imaginary axis is -1. So, minus pi half. So if we just multiply this function by 2 over pi, then we have a function which takes the right boundary values here. And it's also harmonic. Why? Because the argument function is essentially the imaginary part of the logarithm function. So since the imaginary part of an analytic function is always harmonic, we see that this function is harmonic. And now we also know that if you compose a harmonic function with an analytic function, then the result is a new harmonic function. So we can actually move this function back to the unit disk by inserting, instead of W, this function here. So the function we get will be u of x and y will be equal to 2 over pi times the principal argument of 1 plus z divided by 1 minus z. So this is analytic, this was harmonic, so the composition is harmonic then. And of course I've used the notation z is equal to x plus iy here. Also you could now, of course, if you consider this to be a real valuable theory problem, then it could be more convenient to express this in terms of the real variables x and y, which is very easy. You just compute the argument of this complex number in terms of x and y, and I won't do that here, but the result is then that you get the arctangent function of the arctangent function of 2y divided by 1 minus x squared minus y squared, like this. So this is actually the solution to the problem. This will be a function which is harmonic in here, takes the values plus 1 up here and minus 1 and down here. So it could be, for example, interpreted as the electric potential if you have put charges which gives you value 1 up here and minus 1 down here. So this was, of course, a very simple problem because we actually had this argument function ready from the beginning, so to speak. But I'll also now show you a slightly more complicated problem. But before we do that, we need to know something more about Möbius transformations. So let's consider the situation where we have a real line here now and 2 points. And these points now, we call them Z1 and Z2, they are said to lie symmetrically about this line. So in this case, they're actually each other's mirror images, you might say. So the observation we make is that if we draw the real line through these 2 points, then it will intersect the original line here orthogonally. But actually, if you draw any circle through these 2 points here, now, like this, it will also intersect. Orthogonally. So this leads to the definition that you say that 2 points, Z1 and Z2, lie symmetrically about the line or circle C if every line and circle passing through Z1 and Z2 intersects. They intersect C orthogonally. So as long as C is a line, it's quite an easy concept to understand here now. But if C is instead a circle, what will this mean? Well, suppose that we draw this line through the origin here now. Then I say that these 2 points, if we call them P and P star, they lie symmetrically about this circle if and only if the absolute value, well, suppose this is the origin then the absolute value of P here now times the absolute value of P star is equal to 1. And of course, they must lie on the same, they must both lie on the same line through the origin. Otherwise, not even this line would intersect orthogonally here. But in this situation, when you have this condition, then it turns out that every circle through these 2 points will intersect this circle orthogonally. And the interest of this concept with symmetrically lying points about the line or a circle is that it's conserved under Möbius maps. So if you have 2 points which lie symmetrically about this line, for example, and if you map this line onto a circle, then the image points of these two, they will all still lie symmetrically about the image circle. Why is that? Well, it's actually an almost trivial fact, because we know that Möbius maps, they conserve the class of lines and circles. And since they are conformal, they also preserve angles, in particular 90-degree angles. So from this you see that Möbius maps always preserve symmetry in this sense. And this will be very useful now for the construction we will make. So let me start by proving a statement about symmetry about the circle that I just made here now. So here is our circle, and we suppose that these 2 points lie on the positive real axis then. So what we want to prove is that if they lie symmetrically here, then P times P star should be equal to 1. And the method is really then to, instead of trying to do this computation in the unit circle, we simply map the unit circle onto the right, we map it onto the upper half plane. The circle here is mapped onto the upper half plane. And this we can do using the map, well, Z goes to I times, well, let me write it this way. W is equal to I times 1 plus Z divided by 1 minus Z, like this. And then these 2 points will be mapped onto 2 points over here, which lie symmetrically about the real axis. And points which lie symmetrically about the real axis, they must be each other's complex conjugates. So what you get is here really that if you take the image point of P, then you have I times 1 plus P divided by 1 minus P. And if you take the image of P star, then you get I times 1 plus P star divided by 1 minus P star. And then these numbers should be each other's complex conjugates here now. So if you take the complex conjugate of this, it should be equal to that. And now since we have put these points on the real axis for simplicity, you see that the complex conjugate of all this, that's just, you take the complex conjugate of I, which is minus I, and since this is real, you can just remove the bar here now. So now we have this equality then. And if you just divide by I, you see that you get 1 plus P divided by 1 minus P should be equal to minus 1 1 plus p star divided by 1 minus p star. Now, and if you now just multiply by the denominators here, now you get here 1 plus p times 1 minus p star, which is 1 plus p minus p star and minus p times p star. And on the other hand, you get 1 plus p star times 1 minus p, and then the minus sign. So you get minus, and then 1, and then you get plus p star, and then you get minus p, and then you get minus p times p star. And since because of this minus sign, now you see that this term cancels out and that term cancels out. And if you move the 1 over here and this term over here, you just get that 2 2 is equal to 2 times p star. And if you just divide by 2 here, now you get p times p star is equal to 1. So now let's consider a slightly more complicated example of how we can solve the Dirichlet problem using conformal maps. So consider the following situation. We have a circle here. It could be the unit circle then. And inside we have a slightly smaller circle here. Actually, the center of the inner circle will be the point 0.3. And the radius of the inner circle will then also be 0.3 since it passes through the origin. And then we want to find a function which is harmonic in this region and which takes the value 1 on the outside here now, on the outer boundary, and the value 0 on the inner boundary. So how do we find such a harmonic function? Well, this is slightly complicated if you work directly in this setting, but it will become much easier if we map the region conformally onto a region which also has a boundary consisting of 2 circles, but where the circles are concentric. So we really want to map onto an outer circle like this and an inner circle like this. And then we want to solve the problem over here instead. So we find a function which is harmonic here and takes the values 1 on the outer boundary and the values 0 on the inner boundary. So the question is then, how do we construct this map? Well, the idea is now to use this concept of symmetric points. So the idea is to find x1 and x2 which lie symmetrically about both circles. So we want to find points over here which lie symmetrically with respect to both circles then. And when we found these 2 points, we want to map one of them, say x1, onto the origin, and the other one, x2, onto infinity. So why is that? Well, we now know that the property of symmetry is conserved under Möbius maps. So if we find a Möbius map that does this, then these 2 points, 0 and infinity, will lie symmetrically with respect to both circles. But the point which lies symmetrically with respect to infinity, with respect to any circle, is always the center of the circle, which is very easy to see. So then, in the image picture, we then know that the center of both circles must be the point which is symmetric with respect to infinity, that is the origin. So we'll get a picture of this kind. Well, so how do we find x1 and x2? Well, since this picture is symmetric about the real axis, then it's very natural to look for these points on the real axis and actually on the positive real axis. And then we already know the condition for these 2 points to lie symmetrically about the outer circle, namely that the product of these numbers should be equal to 1. But then we also have the condition that they should lie symmetrically about the inner circle. What's the condition for that? Well, actually, we can use the same formula, the same equation that I've deduced, if we're a little bit clever. So consider these 2 points, x1 and x2. To apply this formula, you really need to know that the circle is centered at the origin, which this one is not. But by a translation, we just move the origin to the point 0.3 then. So if we just, this means that for the coordinates that we just subtract 0.3. So then we have 2 points we have a circle which is centered at the origin, but the radius is still wrong. The radius is 1.3, but it should be 1 to apply the formula. So then we just rescale by dividing by 0.3. And then we can apply the same formula as we had here to say that just the product of these 2 numbers should be equal to 1. And you see what we have here now essentially becomes a second order, an equation of second degree here now, because you can just, instead of x2, you can insert 1 over x1 over here, and that will be an easy equation to solve. And the solutions turn out to be x1 equal to 1/3, sorry, and x2 equal to 3. And then, of course, we see that once we're given these 2 numbers, it's easy to find the Möbius transformation which takes x1 to 0 and x2 to infinity. The easiest choice is then to take the Möbius transformation z minus 1/3 divided by 3 minus z. Then you can check that this will be a map that actually does this for us. It takes this region onto the region between these 2 concentric circles, which both have their center at the origin. But we still don't know the radii of the image circles here now. We know the radii here, which is 1 and 0.3, but we have to compute the radii over here. So since both circles have center at the origin, it's enough to take any point on each one of the circles then and measure the distance to the origin. So for the outer circle, we can just take the point 1, map it by f then, and take the absolute value of that, and that will be the radius of the outer circle. And if you just insert 1 here, you see you get 2/3 divided by 2, so this will be 1/3. And for the smaller circle here, you see that you can do the same thing. You just take any point on this circle, map it by f, and measure the distance to the origin. So let's take f of 0 then, because that's a point on this circle. And then you get minus 1/3 up here, and you get 3 minus 1/3 down here. And that will give you 1/9 then. Sorry, you get 0 minus 3 minus 0 down here, and then you get 1/3 divided by 3, which is 1/9. So here are the rate now. This is 1/9, and this is 1/3. Okay, so then we simply have to find now the harmonic function in this region, which takes the value 0 on the circle with radius 1/9 and the value 1 with the value 1 on the circle with radius 1/3. And if you now compute the radial solutions of the Laplace equation, it turns out that they can all be written on the form b of r is equal to a times the logarithm of r plus b then, where r is then the absolute value of w. And so now you have to insert these conditions that r equal to 1/3 should give you that this is equal to 1, and r equal to 1/9 should give you that a times the, well, you should write, perhaps this is the ordinary real logarithm, which we denote this way. A times the logarithm of 1/9 here plus b should be equal to 0. And these equations are very easy to solve then. So what you get is really that WR is equal to logarithm of r divided by the logarithm for number 3 plus 2. Which then means that if you now just instead of r here insert absolute value of w, which is the absolute value of this expression, you get finally the solution to the problem then, that if I now write it in terms of the complex number z, it's 1 over logarithm of 3 times the logarithm for the absolute value of, and if you now, if you insert this value here and simplify, you get 9 times z minus 3 divided by z minus 3. So this is really the solution to the problem. Of course, you can now express this in terms of x and y, and this also in terms of x and y. The formulas will become slightly complicated, so I'll skip that for the moment.